My name is Rohit Srivastav, bearing registration number 23BCE0052. So today I will be presenting on the topic Lattice-Based Cryptography, a quantum-resistant cryptographic approach. In this presentation, I aim to provide a comprehensive overview of cryptographic foundations. So let's dive into it. So here we can see the agendas which we are talking about: introduction to cryptography, classical cryptography overview, quantum computing basics, threat to current systems, need for post-quantum cryptography, introduction to lattices, foundations, lattice problem, learning with errors, and encryption process, DSA algorithm, real world application, advantages and challenges, and comparison between RSA, ECC, and lattices. That is a new one, which is the main topic which we are going to discuss over on, and future scopes like industrial adaptation and other techniques, and finally the conclusion. So let's start. So cryptography is basically the backbone of modern digital security. It ensures the data remains protected when it is stored or transmitted over networks. When we talk about its objective, for instances, we can talk about confidentiality, ensures that only authorized users can get the access of the information. Integrity in the sense of guaranteeing that data has not been altered. Authentication verifies the identity of users or system. Non-repudiations like ensure that a sender cannot deny sending messages. Historically, cryptography started with simple techniques like scissor cipher. Over time, with the rise of computers and the internet, more advanced systems like developed like symmetric encryption uses using a single key, public cryptography, which uses a pair of keys. Today, cryptography is everywhere in online banking and UPI transactions, in HTTPS secure website, in password protection and data storage. Without cryptography, secure communication over the internet would not be possible. This slide gives an overview of two fundamental types of cryptography. That is symmetric cryptography, which uses a single shared key for both encryption and decryption. It is very fast and efficient, which is why it is used in bulk data encryption like AES. But the main challenge is the key distribution. How to do two parties securely share the key? Moving to asymmetric cryptography, it uses two keys, a public key and a private key. The public key is openly shared, while the private key is kept secret. And along algorithms like RSA and ECC are widely used. This solves the key access problem, but are slower compared to symmetric methods. Now talking about limitations, as computational power increases, we need larger key sets to stay secure. More importantly, with rise of quantum computing, algorithm like RSA and ECC can be broken using Shor's algorithm, which we are going to discuss in the upcoming slides. So this is exactly why we need approaches like lattice-based cryptography are being researched to make the system quantum resistant. Like no one can break the system with the help of quantum computing. Okay. So this slide introduces fundamental concepts of quantum computing, which is crucial to understanding why current cryptography is at risk. Starting with qubits. In classical computing, a bit either is 0 or a 1. Okay. But in quantum computing, a qubit can be both 0 and 1 at the same time. It's not like it should be 0 or 1. But here in quantum computing, it can be 0 at the same time, it can be 1. So this is called superposition. This allows quantum computers to process multiple possibilities simultaneously. Like next in entanglement, when two qubits are entangled, the state of one instantly affects the other, even if they are far apart. This creates strong correlation that classical systems cannot replicate. Then we have quantum gates. Just like logic gates, we have quantum gates. So here, quantum gates manipulate the qubits, but instead of simple binary operations, they work on probability amplitudes. Finally, exponential speeds of quantum computers are not faster for everything, but for certain problems like factorization, they are extremely powerful. For example, Shor's algorithm can break easily the RSA encryption techniques. So that's the only reason we are focusing on the lattice-based approach. Okay. So this side is the turning point. From here, the problem is clearly visible. Starting with RSA and ECC, these are the most widely used public key cryptographic systems today. Their security depends on the problem like factorization and discrete logarithms, which are hard for logical computers. They can't do the manual computing or the computing easily. Okay, with the help of that, if we have a very large numbers. Now comes the Shor's algorithm. That is the game changer. It's a quantum algorithm that can solve this problem efficiently. Like no headache for Shor's to make the system, to break the system. They can easily do that. Meaning what takes classical computer thousand of years could be solved, it can solve it within 2 to 3 hours. It's just a cup of tea for them. Okay, and then right now, quantum computers are still developing, but research is progressing fast towards scalable systems. Once they reach sufficient power, current encryption can be broken. Finally, the real world impact HTTPS websites with the help of TLS, we can work on it with the help of Wireshark. I will show it to you in the upcoming slides. So, will not be secure. VPN communication can be intercepted. Like you are using a VPN, but your exact location can be encrypted. It's can be decrypted. Sorry. So it's easy with the help of quantum computing. So digital signature can be forged. In short, the entire digital trust infrastructure is at rest currently. So after understanding threat, now the question is, what's the solution? First, quantum resistant security. That's the very first solution because we have to secure the system first. So we need cryptographic system that remains secure even if quantum computers become powerful. The systems are based on problems that quantum computers cannot easily solve. Second, long-term data protection. Some data needs to remain secure for decades. Attackers can store encrypted data today and decrypt it later when quantum computers become available. Just for instance, we can take an hacker got the encrypted data today and he stores that data, and afterwards when he got the power, like he got the quantum computing, then he can use that data and can decrypt it easily. So this is called harvest now and decrypt later kind of technique, okay, and a very kind of, you can say, serious threat. Third, NIST standardization. NIST is already working on selecting and standardizing the post-quantum algorithm to ensure that future systems are secure and globally compatible. Finally, preserving the trust. Our entire digital world, banking, communication, identity, everything rely on that. Rely on what? Cryptographic, RSA algorithms and all. Okay. So if we are not focusing on that, surely the system going to be break. Now, we move to the core concept, what is lattices? So, which form the foundation of post-quantum cryptography. Starting with the definition, a lattice is basically a structured grid that of point in multiple dimensional space. These points are generated using linear combination of basis vector with integer coefficients. For better intuition, think of it like a crystal structure. We have a crystal structure. The pattern repeats infinitely in all the directions. Like you are going to have one thing, it will go in one direction one time, again different direction one time, third direction is a different time. So you can't like predict that. That's the thing. So each point follows a fixed mathematical structure. Now come the important part, that is hardness. Problems like finding the shortest vector in lattice are extremely difficult. You can't like easily get those. Especially when the dimension increases, this problem becomes practically unsolvable, and this hardness is exactly what we use in cryptography. And if a problem is hard to solve, it can be used to secure data. Unlike RSA or ECC, these problems are believed to be safe even against quantum computers. That's why lattice-based cryptography is considered one of the most or the strongest candidate for post-quantum security. When we got the quantum computers, we can rely on this. Okay. Um, So this slide covers the mathematical backbone of lattices. Starting with vector space and basis, we are working in dimension space. A set of basis vectors define how the lattices is structured. This vector must be linearly independent. Next, the lattice definition. Every lattice point is formed by integer combination of this basis vector. So basically, we are gathering grid using integer scaling. Now the fundamental parallel plate. Think of it as a unit cell of the lattice, just like a repeating block in a crystal, and it's just like crystal structure. The entire lattice can be generated by repeated region. Finally, the determinant as density. The determinant tells how dense the lattice is. Smaller a determinant points are closer denser lattice. Larger determinant points are far apart from the sparse lattice. So this mathematical structure is what allow us to define hard problems. Like if we have a small number, so it can be a closer part. But when the number increases, just like 248 or any of the biggest numbers if we have, so it becomes very tough to predict the number and to get those numbers to be decrypted. That's the thing. This slide is the heart of lattice-based cryptography. From here, the security part starts. Okay, so here the security part starts. So starting with SVP. What is SVP? Shortest vector problem. Given a lattice, we need to find the shortest non-zero vector. Sounds simple, but in high dimension, it becomes extremely difficult. Next, CVP, closest vector problem. Here we are given a random target point. We need to find the nearest lattice point to it. This is even harder than SVP. Now, NP hardness, both SVP and SVP, are classified as the NP hard problems, meaning there is no known efficient algorithm to show to kind of show the exact solution or to solve this in polynomial time. Why it is important? Because cryptography depends on the hard problems. So if a problem is hard to solve, it can be used in securing the data. The final point is security foundation. So here we can use this lattice cryptography based directly on this problem, and importantly, even quantum computers are not known to efficiently solve this. So that's the reason we are following this in quantum periods. Okay, now the most important thing. This is one of the most important concepts you can say, learning with errors. Okay, so starting with the problem setup, we are given a matrix A and vector B. Okay, so B is generated as A dot S plus E mod Q. Here S is the secret we want to find. Okay, now the twist, error term E. If there was no error, this would be simpler linear equation we can easily solve, right? If we know the X and Y value. But because of the small noise, the system becomes very hard to solve. Why it is important? Because this small randomness makes the problem secure. Even with the powerful computer, recovering the S becomes extremely difficult. Next, cryptographic significance, many modern schemes like encryption and key access are built on LWE. Okay, so it's one of the most widely used problem in the post-quantum cryptography. And the final point relies on worst case production. If someone can break LWE easily, it means they can solve the hardest lattice problem. That's why it put very strong theoretical guarantees. Now, this is one of the most important concept, learning with errors, as I said. So here you can see here. So here you can see there are three similar linear equation where one small change is introduced in the constant term. As you can see in the very first image, the term is clearly been seen like number 2x plus 3y minus 1 is equals to 10. So we got very different values. 2x plus 3y plus 1 is equals to 10. So we got a very different value, and 2x plus 1 2x plus 3y is equals to 10. So we got a very different value. So here the small changes like plus 1 minus 1, if you can go with plus 2 minus 2. So this kind of small errors here, E, if you're considering the, as I said in previous slide, as a small E can change the entire thing. So it's not easy to get the final equation and the final solution. So that's the key here. That's the function of LW which I showed here with an example. Okay. So now we are looking at how lattice-based encryption actually work in practice. So step one, key generation, a secret key vector is generated, a random matrix A is created. Then we add a small error for the public key. Public key shared, secret key is kept private, encryption. Step two, that is the message is first converted into a mathematical form, which I showed you earlier, that's like a 2x plus 3y, you can say. And then we perform matrix operation. Fresh noise is added again to ensure security. Like for instance, we can add plus 1 minus 1 in that. And then step 3 started with decryption. The receiver uses a secret key S, which we said. With the help of that, it can predict the noise, like what is the value of noise. So that's the thing. So it can be get the message correctly. Okay. So final parameter selection. This is very important. If parameters are too small, system become insecure. If too large, system becomes slow. So we need a balance between the security and efficiency. Like you can't go for a very bigger one, you can't go very smaller one. You have to be in the medium, or you have to follow the balance. This is a process is used in real world scripts like paper is selected by next. Okay. So the slides explain how digital signature work, especially in post-quantum context. Starting with key generation, every user has a public key and a private key. Private key is a secret key, as you all know, and public key is shared. Okay. So next, signing process. Instead of signing the entire message, we first create a hash. Okay. Then we sign in that hash using the private key. This ensures both integrity and efficiency. Then come verification. The receiver uses a public key to verify the signature. If it matches, it proves the message is not altered. The sender is authenticated. And finally, the post-quantum algorithm works. Here, the post-quantum algorithm, classical signature like RSA will break under quantum attacks, and the new schemes like Dilithium and Falcon are designed to resist the quantum attacks. Cabel is use a kind of secure key exchange. These algorithms are already being standardized and will be used in future secure systems. Right now, it's not using, but we are planning that going to use in future secure systems. Okay. Now here you can see this slide show how lattice-based cryptography is not just a theory; it has a real-world application. Starting with banking and payment system like UPI and online banking require very high security. Lattice-based cryptography ensures that even future quantum attacks cannot be breached. As I said, lattice-based, like the example which I said, like for instance, you can go with the very random values and then you can connect it with it, and then you can get variety of solution, but not the exact solution with the issue of noises. So that's the key here. So next, cloud key management. So platforms like AWS and SUs store huge amount of sensitive data. They're already exploring post-quantum solutions to secure the encryption keys. For instance, you have variety of your keys there in your cloud, like AWS or Azure, and someone is breaking that system and get those keys. To think about all the big platforms will go down if anything happens to that. So that's the only reason they are focusing on the future, that anyone can break the system with the help of quantum computing was who got the solution. So the hence the reason they are focusing on this lattice-based approach. So here, the secure messaging and VPN apps like WhatsApp and VPN services rely on encryption, totally on encryption. Okay, once you got the thing like WhatsApp, if you have a message, okay, and currently they are storing it in an encryption way, but someone got the solution for decrypting that with the help of quantum computing. So think about variety of personal data will be leaked easily with the help of that. So that's the reason they are focusing on lattice-based approaches. Finally, the IoT security devices like smart sensor and IoT systems have limited resources. Lightweight lattice algorithm can secure this disease efficiently. So overall, lattice-based approach is the best thing to go for the post-quantum period. In classical cryptography algorithm like RSA rely on the difficulty of factoring large numbers into their prime components. For example, a number n is generated as the product of two large primes, and while it is easy to multiply them, reversing the process finding those primes is computationally very difficult. Classical computers attempt this by checking possible factors one by one, which become extremely time consuming as the number size increases often and taking thousands of years for large cases like 2048 bits. This computational hardness is fundamental reason why RSA is considered secure in today's system. That's the thing. But but what happened after the post-quantum period? So here the Shor's algorithm came into the picture. It's a quantum algorithm that fundamentally changes the assumption by efficiently solving the factorization problem. Instead of checking the possibilities one by one like classical computer, it uses the quantum principles such as superposition and interference to identify patterns and periodicity in the number. This allows us to factor the large numbers in polynomial time, making what previously infeasible certain practical. As a result, cryptographic systems like RSA and ECC, which depend on these hard mathematical problems, become vulnerable, like highlighting the need for post-quantum cryptography approach like lattice-based methods. That's the thing we have to focus on. Okay. So this is the digital certificate of the SBI website, which I get from. And here you can see there is a public key, and which is used to verify the identity of the server and establish trust. It contains the server's public key and is issued by trusted certificate authority and shown in the chain of trust form DG served to the website. This ensures that the user is communicating with a genuine server and not the attacker. During the HTTPS communication, the certificate is used to perform a secure key access after which encrypted communication begins. However, since the system relies on classical cryptographic algorithm, it's vulnerable to quantum attacks, and therefore future system will adopt lattice-based cryptography for enhanced security. Now, as I said, I will show it to you the Wireshark thing. Okay, so right now all are using the RSA thing like application data. protocol. So here I use a Wireshark capturing the real-time network traffic, and I have applied a TLS filter to focus on secure communication. Each packet shown represent data being exchanged between my system and a server. When I inspect a packet, the data appears as random, unreadable thing, like you can see here, bytes instead of plain text, which indicates that it is encrypted using TLS. This ensures that even if an attacker captures the data, they cannot understand it without decrypting the key. However, the current encryption technique, as I said, RSA and ECC based, so which are used in this process. But it can be break with the help of quantum computing. Like for example, you can take Shor's algorithm. So with the help of that, they can break this and they can get to know what the data has been here and they can decrypt it. So that's the thing. So this slide gives a balanced view, strengths and limitation of lattice-based cryptography, starting with advantages. So it is resistant to quantum attacks, unlike RSA or ECC. It is based on very strong mathematical problem. It can solve variety of mathematical problems, and also it's versatile using encryption signatures and even advanced concepts like homographic encryption. Now the challenges. Okay, every coin has two faces, so challenge will be there. So key sizes are larger compared to classical system, as we all know, and this can be affect performance and storage, especially in low power devices. If the device is not big server, big power devices, so it will affect the working. So finally, implementation consideration. Even if theory is strong, implementation must be secure. Side channel attacks and poor parameter choices can break the system. So overall, lattice-based cryptography is powerful, but practical deployments requires carefully designs. So that's the thing. So this slide compares traditional cryptography with lattice-based cryptography, starting with security strength (RSA) 3072-bit and ECC 256-bit, provide a similar classical security. Lattice-based systems also target similar security levels, but the key difference is lattice-based systems are quantum resistant, as we know. And next, the key size. RSA uses large key. ECC is more efficient with smaller keys. Lattice-based systems have larger key PB, which is trade-off for quantum security. Finally, the performance. RSA is relatively slow, ECC is faster and widely used today. Lattice-based cryptography can achieve good performance, especially with optimization. So overall, RSA outdated in future, ECC efficient but not quantum safe. So lattice is a future proof that can help to with some overhead, but yeah, it's good to quantum, post-quantum period. That's the thing. So this slide focus on future direction of lattice-based cryptography. So starting with NIST standardization, NIST is currently finalizing the post-quantum algorithms. So once realized, this will be adopted globally across industries. NIST integration with AI and IoT feature system with highly integrated lattice-based cryptography will ensure secure communication in this environment. Then hardware acceleration, one major challenge is performance. To solve the specialized hardware is being developed to speed up the latest operations, finally growing the ecosystems. Libraries like Open, Quantum Safe are making implementation easier. And this is the accelerated research and real world adaptation. So overall, lattice-based cryptography is not just a theoretical concept, but is actively moving toward real world deployment at the scale. So as we conclude, one thing has been clear, quantum computing is not a distant possibility. It's approaching reality, right? So the cryptographic systems that we rely on today, such as an RSS, RSA, and ECC, will eventually become vulnerable. Lattice-based cryptography offers a powerful and practical solution, combining strong mathematical foundation with quantum resistance. With ongoing standardizations by NEST and increasing the industry adaptation, transition towards the post-quantum security has already begun. So the key question is no longer if we should adopt it, but how soon we can implement it effectively. So that's the thing. So with this word, I convey my presentation to you all. Thank you so much. Thank you.